Hello students, so welcome to this particular lecture on the skewed inverter. So till now we had seen an inverter characteristics, the CMOS inverter, which is made up of the PMOS and NMOS transistors, where the betas of the PMOS and NMOS were same, and thereby we were able to evaluate the current, the intersection points, which was then put it into the transfer characteristics. So if you remember, the intersection points came from having the current and the voltage characteristics of the PMOS intersecting at that of the current and the voltage characteristics of the NMOS. So for the given input voltage along the voltage output voltage line, the current points which were intersecting, so those became the solution points for the CMOS inverter, which is made up of PMOS and NMOS transistors. So those intersection points gave us the input voltage. I mean, given the input voltage, gave us those intersection points gave us the current as well as the output voltage values. So those particular points were then put it into the transfer characteristics, which is made up of V out in the y-axis and then V in the input voltage in the x-axis, and then thereby the transfer characteristics was drawn for the CMOS inverter. So this is what we had seen in the last lecture. So today in this particular lecture, we will go over slightly modifying. If we have a modified inverter in the sense if the width of the PMOS or NMOS is different than that of the other transistors, then the betas, if it is not same, what is likely to happen to the transfer characteristics? So that's why if the betas are not same, that is called as a skewed inverter. If the betas are same, then it is called as an unskewed inverter. So the unskewed inverter is what we had seen in the last lecture. And today we are going to look into the skewed inverter where the betas will not be the same. Okay. So moving ahead. So just a revision of what we had done in the last lecture is the transfer characteristics of the V out versus the V in is drawn. These were the intersection points. A, B, C, and then D, E, and F were the intersection points which we had clearly drawn, where the current of the PMOS and the current of the NMOS were actually intersecting, and then those points we labeled it as A, B, C, D, E. Right, and from those particular points we got two values. One is the current value, and then the output node, values, voltage values for a particular input voltage. And we had chosen six input voltages. One is the 0 volts, second is 1 volts, 2 volts, 3 volts, 4 volts, and the 5 volts, and thereby we get these six intersection points. The seventh one, which is a G point here, is the intersection points for the input voltage of 2.5 volts. Right, when the betas are same. For the 2.5 volts, we realize that the G point is actually not a single point. It is actually a series of points, because the saturation currents. So if I want to draw the PMOS, so this is my PMOS. For the current versus the V out of the inverter, and for the NMOS, this is the value. This is the particular profile. So this is the PMOS profile. So let me draw, use a different color. So this is PMOS, and this is NMOS. Right. So these intersection points, the series of intersection points, is what is giving me this particular profile. So in fact, I've drawn it a little bit kind of a slope line. It should not be a slope line. It should be a straight line along the point G. Right. So the transfer characteristics should actually look something like this, and then something like this. All right. So that is the series of intersection points. So I've picked one point of G where the input voltage is 2.5, where we'll get the output node voltage, a series of values. So that is called as a transition region. Right. So just to summarize the points A, B, C, and then D, E, F, what we are saying is the point A here. So if you remember the point A in the previous slides or the previous lecture, you will notice that the point A was on the extreme side of the IV characteristics. So the extreme side of the IV characteristics represents, no, the point A was actually touching the x-axis line. So the point A was when NMOS transistor was in cutoff. So I'm going to write it as NMOS was in cutoff. Okay. And PMOS, we had it in linear region. So the intersection of those two current lines gave me the point A. Similarly, point F. So this particular point is exactly the opposite, right? Exactly the opposite, where I had, so F point was actually lying on that zero voltage point, right? In the IV characteristics profile. So this F point is where the PMOS is in cutoff, and NMOS was in linear region. All right. Right. So point A, so let's come back to point A. So PMOS is in linear region, NMOS is in cutoff is what we are claiming. So NMOS is in cutoff. No, let's try to evaluate or validate whether our claim is correct. NMOS should be in cutoff for point A. So the point A is a point where the input voltage was zero. Input voltage was zero, so that means the NMOS VGS value was zero, and that thereby it is validated that the NMOS will be in cutoff. PMOS, although its line looks like a linear region, so in fact if the V input is 0, VGS turns out to be minus 5 volts, VGS turns out to be minus 5 volts. Is that correct? So if I draw the PMOS, so let me draw the PMOS, and if V input is actually 0 volts, S is nothing but VDD. So this is nothing but, we had considered 5 volts here, and this is my output voltage, right? And then we have this NMOS, right? So let's forget about the NMOS time being. We have validated NMOS should be in cutoff for input is equal to 0. For PMOS, I'm claiming that it is in linear region, but let me have a look at it. VGS, right? This is G for the PMOS, this is S for the PMOS. So VGS turns out to be minus 5 volts. That means VSG is plus 5 volts, much above than the VT of 0.3 volts, or rather, much negative than that of the minus 0.3 volts. Thereby, this PMOS transistor will be on, right? So whenever it is, the VGS or with respect to VSG, if it is VSG is much greater than the mod of VTP, which is 0.3 volts, then we say that the PMOS is on. So it means that it should be in either linear region or the saturation region, right? So at point A, the output voltage node, what I have stated here in the table, it is 5 volts, and this 5 volts is actually coming from the intersection points which we had seen in the previous lecture, right? So the point A, which is actually on that particular x-axis line at that particular VDD point, and we got the V out to be 5 volts. So this is actually 5 volts. Although the PMOS region is in linear, so this particular PMOS, I am writing it as to be on transistor, which is also in linear region, right? The output voltage is 5 volts, VDD is 5 volts. So the current here, that is flowing from the source to drain should be 0, right? ISD should be 0, because both the potentials, both the terminals have a potential of 5 volts. So both the terminals have the same potential. So the current VDS or VSD for the PMOS is actually 0, right? So the linear region current, whatever we have the expression, if I put VSD to be 0, I'll get the current to be 0, right? So our claim of PMOS to be in linear region, right, is validated, although the current value is 0, and this is what is shown in this particular table, right? So let me pick a different color. Similarly, for this particular point F, right? For point F, we say that our claim is NMOS is in linear and PMOS is in cutoff. PMOS is in cutoff because V input is 5 volts. If V input is 5 volts, VSG or VGS is 0, right? So it is not, it is not above 0.3 volts or not beyond minus of 0.3 volts in whatever terms you take, whether it is VSG or VGS. So the PMOS is in cutoff, so that is validated. So this part is validated. NMOS is in linear region. Of course, the V input is 5 volts, so VGS for the NMOS is greater than 0.3 volts, and thereby the NMOS will be in, will be above the cutoff region. So it will be either in linear region or the saturation region. Right. Again, if I pick this V output voltage, it is 0 volts. So the output voltage is now 0 volts. The other terminal of the NMOS is also ground. So the VDS potential, so the potential difference between the drain and source of the NMOS transistor is the same, or rather the potential difference is 0. So the current that is flowing in the NMOS transistor will now be 0. Right. So that's what we are getting here. For the other points, for the points B and C, if you remember, the B and C points was actually closer to the 5 volts. So it was on the right side. B and C points were on the right side of the IV characteristics, and the D and E points were actually on the left side of the IV transfer characteristics, right? So the B and C points were on the right side. What it implies is the B and C points were the intersection points coming from the linear region of the PMOS and the saturation region of the NMOS, right? So the saturation region of the NMOS, so that's why I have written the current of saturation of the NMOS, equated it to that of the linear region of the PMOS current, right? For both B and C. And similarly for D and E, for an unskewed inverter means when the betas are same, the D and E are symmetrically on the opposite side as that of B and C. And D and E, which is closer to the 0 volts now, what we can say is the D and E is, those points are arrived from when the PMOS is in saturation region and NMOS is in linear region, right? So those two current, in the one in the saturation and another one in the linear region, if we can find out the solution, then we will get the points D and E, right, for that particular values of the input voltage, right? So this particular profile, this particular region above the transition region, so this is, I'll call it as the transition region. So above the transition region, all right, this is where we will have the PMOS to be in linear region, right? And then this particular region below the transition region, so the points D, E, F is when the NMOS will be in linear region, right? And during the transition region can be characterized as the the intersection points of in the IV characteristics, where both the transistors are in saturation region. So in this particular region, it is both the PMOS and the NMOS are in saturation region. So I'm going to write it as P and N as saturation region. So hope this is clear. So this is the transfer characteristics of the unskewed inverter. Okay, so let me proceed further. So if I have beta P is equal to beta N, so it's an unskewed inverter, we have this particular transfer characteristics. This transfer characteristics is more appropriate because now this becomes a very, very straight line, right? So the point G, the G point, whatever I had drawn the previously, which is actually nothing but for an input voltage of 2.5 volts, it will give me the series of these points, right? There is no one particular G point, right? It should give me a series of the output values, for a particular input voltage value. So if I apply an input voltage of 2.5 volts, I might get this particular value as the output. I might get this particular value as the output voltage. I might get this one as the output node voltage. I might get this one as the output node voltage. Okay. Now what happens if the betas are different? So that is what is the crux of this particular lecture. So what we are going to do is establish a different label called as skewing ratio. So the skewing ratio is nothing but the ratios of the betas of the PMOS and the betas of the NMOS, right? Remember that the betas are nothing but a function of the width. So the PMOS width and then the NMOS width Although the skewing ratio is nothing but the ratios of the betas of the PMOS and NMOS which are used to construct the inverter. Right, and then it may be used, I mean, we can have a skewing ratio of for a different combinational circuits for a different standard gates also. That we will see, look into the in some of the future lectures. But at this point of time, the betas of the inverter, so the betas of the PMOS transistor and the betas of the NMOS transistor, the ratio of that, which is used for drawing or designing the inverter, is called as the skewing ratio. If R is equal to 1, it is called as an unskewed ratio. That means that the betas are same, and that's why it is called as an unskewed inverter. If R is smaller than 1, that means beta P, the PMOS beta is less than that of the NMOS beta, right? And that is called as a low skew. And if beta P, if the skewing ratio is greater than 1, that means that the beta P is greater than beta N. So that is called as the high skew ratio. All right. So if R is greater than 1, it is called as an high skew. That's what is mentioned here. That means that the beta P is greater than beta N. Standalone, if it's not an inverter, if I have a standalone PMOS transistor, so let me draw a standalone PMOS transistor. So PMOS with a bubble, and then let me say that this is input, this is my source, and this is I'll just ground it instead of connecting it to the NMOS transistor, right? Because it's a standalone transistor, right? And similarly, I will draw an NMOS, which is nothing but V input, again a VDD here, and then a ground. Of course, this will be drain for the NMOS, and then this will be a source for the NMOS, right? So if I have this beta P to be more than beta N, so the current here, what I'm drawing from the PMOS, so the current of the PMOS will be greater than the current of the NMOS. So that's what I've stated here, right? But if I actually put these two transistors together, so let me pick up another colored pointer. So if I have these two transistors, and and then this particular transistor, so if I disconnect this ground and VDD and then connect it here, the currents of these two transistors which are in series should be same. All right. Although the betas are different, right? If I connect it in series, I will get the same current, right? So that's why I've written, if I have a betas to be different, and as a standalone transistor, the current what we are expecting from the PMOS and what we are expecting from the NMOS, the PMOS current is likely to be greater if I apply the same voltage, same VGS value. In fact, same VGS value, and then the same VDS is given, then I'm expecting a more current from the PMOS. Right, so again, just to reiterate that, the same expression I have written. So the PMOS current is likely to be more in a standalone transistors. So that's what I have written. But when they are connected in series to form the inverter, we have to satisfy the Kirchhoff's current law. So this particular value, so the currents being same has to satisfy, right? Even when the betas are different. So standalone, the currents will be different, but when they are put together in an inverter, the currents will be equal. And we will get, of course, very similar to what we had seen in the last lecture. We will get the intersection points. If we apply the input voltage of 0, we will get the intersection point of A. If we apply the input voltage of 1, we will get the intersection point as B. If we apply the input voltage of 2 volts, we will get the intersection point as C. If we apply the input voltage of 3 volts, 4 volts, and 5 volts, we'll get the intersection points as D, E, and F. Of course, those intersection points, that position of those points in the IV characteristics. In the IV characteristics means what we had seen in the last lecture. Let me draw a different one. So the PMOS current, PMOS current, and if I draw the NMOS current, something like this. So this intersection points, the intersection points here, and somewhere here, this particular point might be different now. It will be different now because it is an unskewed, it's a skewed inverter. So the betas are changed. So the betas are not equal. So those intersection points where we had the betas to be same, so those positions or the intersection points will be different now. So hope you are able to understand. Okay, so I've drawn this particular profile when the beta p is actually twice that of the beta n. And one way to do this is if it is twice, or rather, if beta p has to be equal to beta n, whatever we had seen in the last lecture, we wanted to make this PMOS width to be twice that of the NMOS width. And if I want to make the beta p is equal to 2 times the beta n, I will make my the PMOS width to be 4 times the NMOS width. Okay, and that's where we will get the beta p to be equal to that of twice that of the beta n. And if I draw the IV characteristics now, although I was not able to, for this particular V input of 0 line, for the PMOS IV characteristics, I did not get the space. But, this particular linear region is sufficient enough, and it will actually proceed. So if I pick the blue color, so if I, somewhere here it will draw. All right. So coming back to my black pointer, for V input of 1, I get this particular blue line. For V input of 2, I get this particular blue line. For V input of 3, I'll get this particular blue line. And then V input of 4 and V input of 5. For V input of 5, the PMOS will be in cutoff. So the line, the IV characteristics line will be nothing but the x-axis line. Similarly, the input voltage, the IV characteristics of the NMOS transistors. For V input of 0 is this particular x-axis line. V input of 1, we have this particular line. V input of 2, I have this particular line. V input of 3 is this particular line. V input of 4 is this particular line. And then V input of 5 is this particular current line. Notice that earlier, for an unskewed inverter, V input of 0, the saturation current of V input of 0 was matching with the saturation current of the V input of 5. Right? And similarly, the saturation current of V input of 1 was matching with that of the saturation current of V input of 4. What it really means is the saturation current is nothing but the highest current, the constant value. So those levels, the constant values of the V input of 1 in the PMOS and V input of 4 of the NMOS are actually matching. Right? V input of 1 is actually nothing but VGS or VSG of PMOS to be 4 volts. And V input of 4 for NMOS is nothing but 4 volts. So if I have the VSG or VGS to be same and betas to be same, then I am likely to get the same current. But now, because the betas are different, the saturation currents now, the maximum level of the currents for the PMOS and for the NMOS are different now. Right? And that's why we will get the levels to be different. So in that particular case, I'll still be able to get the intersection points of BC, or rather A, B, C, D, E, F, right? It is still the same in a graphical analysis for the same input voltage, for the input voltage of 0, wherever the current of the PMOS intersects with that of the current of the NMOS, we will get this particular point A. Similarly, for input voltage of 1, wherever the PMOS current is intersecting with that of the NMOS current, we will get this particular point B. And similarly, point C for the input voltage of 2, point D for the intersection point D for the input voltage of 3, point E and point F for the input voltage of 4 and 5 volts respectively. So it is very, very similar to what we had seen for an unskewed inverter. But if you look into this closely, the points B and C for an unskewed inverter was symmetrically placed, was symmetrically a mirror image of those positions in the IV characteristics. Whereas in this particular case, because of the skewness of the betas, the current magnitude of the current is slightly skewed now of the PMOS and NMOS in the IV characteristics, and thereby the positions of the BC right, doesn't match to the positions, of the E and D. What I mean by the positions means the levels of B and C doesn't match to the levels of E and D. Right, E and D are slightly above than that of the B and C. Right, so for the betas to be higher, the D and E points, right, are slightly higher. Not only higher, they are slightly away from the 0 volts than when it was in the unskewed inverter. All right, and C and B points, right, in this particular case, when the betas was, is twice that of the beta N, the beta PMOS is higher than that of the beta of NMOS, the C and B points are now actually closer, much closer to the 5 volts. E and D points are now slightly moving away from the 0 volts. Okay, so this is something, once you should be able to draw it for the unskewed inverter and the skew inverter, you should be able to notice it, right, and appreciate it. Okay, hope this is understood. So moving ahead. Okay, so one more point here I wanted to emphasize is, in an unskewed inverter, the point G, right, if I applied in an unskewed inverter when VDD was 5 volts, if I apply input voltage of 2.5 volts, I should be able to get the series of the intersection points, right? So a series of intersection points, which means that the PMOS saturation current is intersecting with that of the NMOS saturation current, and then those particular intersecting series points where is nothing but our transition line in the transfer characteristics, right? In this particular case, when it is now skewed, the standalone PMOS current will be higher than that of the standalone NMOS current. So in fact, the standalone PMOS current, the standalone PMOS current in the saturation region, if I look only into the saturation region, it will be higher, right? So what it means is, for an input voltage, right, which is less than, or rather, for the input voltage, for an input voltage to be higher than 2.5 volts, for an input voltage about 2.5 volts, or somewhere between 2 and 3, or closer to the 3 volts, I should be able to draw a line of the current line of the PMOS, the current line of the NMOS, and at that particular point, we should be able to establish a series of the intersection points in the saturation region, right? So if I draw actually in this particular skewed inverter of beta P is equal to twice that of beta N, and if I draw the 2.5 volts input voltage and the PMOS current line and then the NMOS current line, I will actually not get the intersection point. In fact, I will get only one intersection points. I'll get actually only one intersection point and not a series of the intersection points. All right. In fact, that particular intersection point, if I draw V input of 2.5 volts, that particular intersection points will be the point where the PMOS will be in the linear region and NMOS will be in the saturation region. So in fact, the 2.5 point will actually be shifted somewhere along this particular side, right, where it is, the intersection point is closer to the 5 volts, right? Because it is skewed now, it is the threshold or the transition region doesn't fall in the input voltage of 2.5 volts. What I'm saying is, it will be now, if I want to draw the seed, or if I want to derive the series of the intersection points, it will be the input voltage which is closer to the 3 volts and higher than 2.5 volts. And we will look into it, what exactly will be that particular input voltage where we will get the series of the intersection points. Okay, so in the last slide we had got the points of A, B, C, D, E, F. So reflecting those points into the output versus the input profile, this is what I'll get: A, B, C, and then I'll get D, E, F. Right? Remember that A, B, C is now much closer to the 5 volts. So it is, in fact, if I look into this particular transfer characteristics with respect to the transfer characteristics of an unskewed inverter, this point B has slightly moved slightly moved above its position when it was in the unskewed inverter. It is slightly moved above, but yet it should be lower than the 5 volts. And similarly, C point slightly moved above. D and E points are now closer, or rather, it should be away from the zero volts, right? Again, so this particular D point and E point away from the 0 volts, so it is slightly moved above its own position when it was an unskewed inverter. All right. So what it really means is, if it is an high skew inverter, right? High skew, which is nothing but the ratios, the skewing ratio is greater than 1, then the transfer characteristics is actually shifted towards the right. Right? And the inverter threshold voltage, because I have done some calculation, which we will see later, it actually moves from 2.5 volts to 2.88 volts. So don't worry about this particular value. You should be able to calculate it. In the future slides, we will derive that particular expression. But for time being, let's assume that this value is correct, 2.88 volts. For the skewing ratio of 2, then this particular transfer characteristics around the 2.5 volts, it has been shifted to 2.88 volts, right? So the more regions are there in this particular transfer characteristics of the output versus the input, for a more value of the input voltage, the output stays at 5 volts, closer to 5 volts. And for the less points of the input, right, for the less points of the input, it stays at 0 volts or closer to 0 volts. The beta P, if it is more than beta N, in this case it is 2, right, beta P is more than beta N, what it's doing is, it is pulling most of the input voltage to the 5 volts. And beta N, because beta P, which is more dominant, so the PMOS is more dominant, so it is going to pull away most of the points closer to the 5 volts, most of the input voltage closer to the 5 volts. And the less number of input voltage, the NMOS is able to pull it closer to the 0 volts. And similarly, if beta N is greater than beta P, right, like similarly, if beta N is greater than beta P, then beta N, or the NMOS, is more dominant, so it is going to pull most of the input voltages closer to the 0 volts, right? And then most of so PMOS is a weak transistor in that particular case, and so it will have so it will be able to push less number of input voltage to the 5 volts.